Okay, final section on stereochemistry. And stereochemistry plays a very significant role in biological systems. As we've already seen with the enzymes, our active sites are stereo-specific. Certain things will fit into them. It's important we think about things in terms of 3 dimensions. If you think of your hand going into a glove, your left hand fits your left glove, not the right glove. And enzymes, as you see here with their active sites, will only read certain structures, certain 3-dimensional arrangements. And so you can see here that alpha amylase will break down alpha 1,4 glucose, but it won't be able to react with beta 1,4 glucose. So stereochemistry in proteins is arising because we've got chiral carbons in all examples except for glycine, which has got 2 H's attached. So a chiral carbon is a group that's got 4 different groups attached to it, and you can see here how to maybe draw it out. These 2 in the plane of the page, this one coming out, that one going back in. It's a mirror plane here, and just copying it on this side, I've got my 2 forms of an amino acid down here. And I can also look at that in other biological substances where I've got a carbon with 4 different groups attached. I can also start to think about stereochemistry for those. In lipids, we need to be thinking about cis-trans isomerism, where we can have nice straight chains like this. If we've got a cis bond in there, then it kind of bends back on itself. You can see the packing would be less, the London dispersion forces would be smaller, and as a result it's going to have a lower melting point. So removing some of these is going to raise the melting point because it's going to help straighten out the chains. And we can hydrogenate fats by using hydrogen with a nickel catalysts. So that can affect also shelf life, because if we've got these double bonds, they're maybe going to be more susceptible to rancidity. Carbohydrates, well, we maybe need to learn the terms alpha and beta glucose here. If we look at this carbon in our cyclical structure, if it's alpha, the OH is down. If it's beta, the OH is up. And you can see that the alpha glucose here is going to polymerize to give us starch and glycogen, but the beta form is going to give us cellulose. Right, so we get these long linear cables, and this is a more kind of spiral compact structure because of how they bond together. Here, with the cellulose, we're unable to break that down, and I think in a previous unit we talked about cellulose being an important part of the diet in terms of being dietary fiber. So there we are, we haven't got this enzyme cellulase. Lots of animals will eat grass. We can't break down that beta glycosidic link that's forming the chains, and as a result it forms dietary fiber for us, but it does have significant health benefits from eating it. Last place to talk about stereochemistry, and again it's a cis-trans piece, is for vision. So rhodopsin in the eye comprises opsin and retinal. So opsin's this big protein structure. Now the retinal starts off in its cis form, and it's bonded to the opsin, and then when light comes in contact with it, what happens is that that cis gets changed to trans, and that trans form can no longer bind to the opsin and it falls off. And as that falls off, there's a nerve impulse triggered, goes off to the brain, and it's a way for us to sense light being present.